The cosmic crisis. When our best theory fails. Imagine our most trusted map of the universe, the brilliant framework guiding astrophysicists for decades, suddenly pointing in two conflicting directions. This isn't science fiction. It's the shocking reality confronting cosmology today. We're witnessing a profound crisis, a moment where the standard model of cosmology, known as lambda CDM, appears to be fundamentally flawed, predicting a universe that starkly contradicts what we observe. At stake is our very understanding of cosmic evolution, from the Big Bang to the fate of everything. The heart of this crisis pulses with a critical contradiction called the Hubble tension. Picture two cosmic speedometers giving wildly different readings for how fast the universe is expanding. Measurements using the cosmic distance ladder, relying on incredibly precise observations of celestial objects like Type A supernovae and Cepheid variable stars in our galactic neighborhood, reveal an expansion rate significantly faster than expected. Yet, when we peer back in time to the universe's infancy, using the cosmic microwave background, that faint afterglow of the Big Bang, the predicted expansion rate is distinctly slower. This isn't a minor calibration error. The discrepancy is statistically massive, defying easy dismissal. Crucially, powerful new eyes like the James Webb Space Telescope are not resolving this tension. They're intensifying it. Recent findings in 2025 strongly support the faster expansion rate, prompting leading physicists like Dan Skolnick to declare, "The tension now turns into a crisis. Our model of cosmology might be broken." The JWST has compounded the problem by spotting galaxies in the very early universe that are far too massive, bright, and mature than LCDM allows. But the Hubble tension is only one symptom of a deeper malaise. Consider the cosmological constant problem, often termed the vacuum catastrophe, arguably the most staggering failure of theoretical prediction ever. Quantum field theory, our immensely successful framework for particle physics, calculates the energy bubbling in the vacuum of empty space. This vacuum energy density should drive cosmic expansion. However, the value predicted by quantum theory is astronomically larger, by a factor of 10 to the 120, than the actual energy density observed acting as dark energy in cosmology. Grasping the sheer scale of this error is mind-bending. Imagine measuring the diameter of our entire Milky Way galaxy and being off by the width of a single bacterium. Or measuring the observable universe and missing by just a human hair. These analogies, as dramatic as they sound, fail to capture the absurdity of a miscalculation spanning 120 orders of magnitude. This chasm exposes a fundamental schism between our two pillars of physics, Einstein's general relativity governing gravity and the cosmos on vast scales, and quantum field theory ruling the subatomic realm. Adding to the puzzle is the profound mystery of the universe's dominant constituents, dark matter and dark energy. Together, they make up a staggering 95% of the universe's total mass energy content, yet we know almost nothing about what they truly are. Dark matter's gravitational grip is essential for explaining why galaxies don't fly apart and how cosmic structures formed, but decades of searching have yielded no direct detection of its particles. Dark energy, responsible for the universe's accelerating expansion, remains an enigma beyond its label. Its nature is completely unknown, existing merely as a placeholder in Einstein's equations, a fudge factor he initially introduced to force a static universe, only to later discard it as his biggest blunder when expansion was discovered. Ironically, its reintroduction as dark energy to explain resurrected the cosmological constant problem on an even grander scale. This convergence of contradictions, the Hubble tension tearing at our timeline, the vacuum catastrophe highlighting an incomprehensible theoretical rift, and the utter mystery of dark matter and energy signifies a pivotal moment. Physics isn't just facing complex puzzles, it's grappling with the possibility that lambda CDM, our most successful cosmic model, requires not just tweaking, but a profound overhaul. The universe, it seems, is demanding a revolution. We stand at the precipice of potentially rewriting our understanding of gravity, energy, and the very fabric of reality itself. Beyond the breaking point, chasing shadows in the cosmic dark. So, where do we go from here? With LCDM cracking under pressure, physicists are embarking on a monumental quest, probing the universe's deepest shadows for answers that could rewrite the rules of reality. This journey isn't about small adjustments. It demands radical rethinking, challenging foundational pillars we once considered unshakable. The Hubble tension's stubborn refusal to vanish suggests our cosmic timeline itself might be flawed. Could the very early universe have experienced a brief explosive phase we've completely overlooked? One compelling avenue is early dark energy. Imagine a mysterious, ephemeral force field that flared into existence within the first few 100,000 years after the Big Bang, accelerating expansion faster than LCDM allows during that crucial window. This extra push could align the CMB-based predictions with the faster expansion rate we measure locally. However, EDE isn't a magic bullet. It must delicately switch off without leaving detectable traces in the CMB's intricate polarization patterns, a fine-tuning challenge that makes many theorists uneasy. If ED exists, why did it vanish? What quantum field could behave this way? The absence of clear answers underscores how deep the mystery runs. Meanwhile, the vacuum catastrophe's staggering 10 to the 120 discrepancy forces an even more profound confrontation. Some propose radical modifications to quantum field theory itself, suggesting that vacuum energy might somehow gravitate differently than ordinary matter, effectively canceling out its colossal predicted effect. Others explore the controversial multiverse hypothesis, where our universe is just one bubble in an infinite froth of realities, each with random physical constants. In this view, we observe a tiny cosmological constant purely by chance, because only in such a bubble could galaxies, stars, and life emerge. But is this science or untestable philosophy? The lack of experimental pathways to verify such ideas highlights the gulf between elegant mathematics and tangible proof. Then there's the enigma of modified gravity. What if Einstein's relativity, while brilliant, breaks down at cosmic scales? Theories like MOND attempt to replace dark matter by tweaking gravity's behavior in regions of extremely weak acceleration. While MOND explains some galactic rotation curves, it struggles catastrophically with galaxy clusters and the CMB. More sophisticated offshoots, like relativistic MOND variants or emergent gravity, remain highly speculative. Yet, the possibility that gravity itself operates differently on vast scales, perhaps due to unseen extra dimensions or quantum entanglement woven into space-time, can't be ignored. Especially when dark matter particles remain frustratingly invisible despite decades of sophisticated searches in deep underground labs like Xenon NT and Lux Zeppelin. The hunt isn't just theoretical. It's propelled by a new generation of cosmic observatories. The James Webb Space Telescope, already intensifying the crisis, is scrutinizing those impossibly mature early galaxies. Are their immense masses and complex structures real, or could unknown dust properties or exotic stellar populations be tricking our instruments? Upcoming missions like ESA's Euclid and NASA's Nancy Grace Roman Space Telescope will map billions of galaxies across cosmic time, charting the universe's expansion and structure growth with unprecedented precision. Will they deepen the Hubble tension or reveal subtle inconsistencies pointing to new physics? On the particle front, experiments at CERN's Large Hadron Collider and next-generation neutrino observatories hunt for signs of sterile neutrinos or weakly interacting massive particles that could finally unmask dark matter. Even more exotic possibilities are in play. Could dark matter interact with itself through unknown forces? Could dark energy evolve over time, growing stronger or weaker? Each question peels back another layer, revealing how much we've taken for granted. This convergence of dead ends isn't despair, it's exhilarating. History shows physics thrives on such ruptures. Newtonian mechanics collapsed at extreme speeds and tiny scales, birthing relativity and quantum theory. Today's crisis echoes that transformative energy. As pioneering cosmologist Wendy Friedman emphasizes, discrepancies are where discoveries happen. We're witnessing the dawn of a potential paradigm shift, where answers may lie not in patching old models, but in embracing radical syntheses, perhaps linking gravity and quantum mechanics through string theory or loop quantum gravity, or redefining the vacuum as a dynamic quantum foam. The universe isn't broken, our map is. And in redrawing it, we may uncover wonders beyond our wildest imagination, new dimensions, cosmic symmetries, or even clues to existence itself.